what you're really doing is you're charging up this capacitor when you get to here. And then if you don't take too much current off, some of it will actually discharge down, and then the next bump will come along and charge it up, and then it'll discharge down, and you know, basically what you're going to get is something that still has an alternating current component in it, but the ripple could be low enough. And if you make the capacitors big enough so that when you charge them up, very little, if any, comes out. You know, like less than 1% of the voltage. So if you have 12 volts, you know, less than 0.12 volts, you won't even hear it. It'll be essentially non-existent. So this is the filter section, power supply, that takes the ripple out and gives you a pure DC. There's your zero axis, 12 volts, and it's constant. What you had here to start with is this, what you have, and then you went to this, and now you got that. Pretty good. Most of the time that we're done, because you build these power packs that come with your appliances, you know what the load is. You can make sure that you will get 12 volts at some current like 1 amp, and everybody will be happy. Now if you took less than an amp, the voltage might sneak up to 13 or 14. If you took too much current, more than an amp and a half, maybe it might drop down to 9 volts. So depending on what the load looks like, that might be an issue. Now if I want constant voltage regardless of load, or within a certain range of loads, I have to do something about that. So we come up with a fourth stage to this guy, and he's going to be called a regulator. And you're going to get introduced to our good friend here called the transistor. And another variation of the device you know about called the diode, but this guy's got a special characteristic. This guy is a Zener diode. And I'll show you what that's all about. And I have to do a little other trickery here. I put a little resistance here and connect it here. Why? I've actually got a forced current to flow through this Zener diode to make him do his job. I don't want to erase too much here, so let me just make space in this area. That curve, that shows what a diode does. Doesn't matter which. I set the current up on top first, and thinking for a second which way I want to do this. Yeah, I can give it that way. And the voltage on this axis. And this guy had a characteristic where, you know, you either get all current, or no. I know I did it like that before, but the same idea applies. You get all current and no voltage, or if you have voltage, you have no current. In the Zener diode case, if you go negative on the voltage axis, it starts doing this. It has a breakdown voltage. And in this case, I'm going to pick a device that's got a breakdown voltage of minus 12 volts direct current, meaning put these little wings on it to indicate that it's not a normal diode, it's a Zener diode. And they compound in the chemistry. They add a doping, they call it, element to the silicon. Usually it's gallium or arsenic, in such a proportion that when you are trying to force the current to go in the wrong direction, if you put the voltage up to a certain level, like in this case 12 volts, 12 VDC, I'm just arbitrarily picking that. Zener diodes come in all kinds of voltages, but usually standard power supply voltage is like 5 volts, 12 volts, 18 volts, 24 volts, whatever. When you get to that point, this thing will start conducting in the wrong direction. And the reason it does that is to set a voltage standard. It basically becomes the device that determines what voltage we want that power supply to be regulated to So what we're doing here is we're putting a resistance, and it's connected here, and it forces, you know, the resistance is such that there will be current flowing through here, and you will have 12 volts at this point. Now what's the transistor doing? When we get into the transistor in more detail, what you'll find is there's a 0.7 of a volt drop between the so-called base and this emitter. And what will happen is this guy will follow whatever voltage is here will pretty much determine what the voltage is here. So if I have a 12 volt zener, there will be like 11.3 volts there. You know, basically I can set the voltage where I want it to be. And what will happen is this guy will change the drop across this junction so that you will get a constant voltage here, no matter how much or how little current is flowing through. I don't want to say how much or little without limits. You know, within a given range, it will give you the same voltage regardless of how much current you're drawing, so that you can put big devices and little devices and have a pretty reliable power supply. And that's the whole Follow X right there. That is a power supply. It's your first circuit, guys. Congratulations. You designed it, built it, you know, have fun with it. It will work right. Very useful. And just about every electronic system has to start with one of those because they run on direct current. So if you're going to build something that plugs in the wall, you're going to have to convert what comes out of the wall to that stuff. Usually a DC voltage at some level or multiple DC voltages. Meaning you might have a primary winding here on this transformer and secondaries that produce different voltages, like 18 volts, 30 volts, and who knows what else, maybe just 6 volts. You see that, you know, I got an intercom circuit that was taking apart, built by Newton, that had like 6 different voltages for different stages. And that part worked fine, but the regulating circuit they put in there was constantly burning up. It couldn't handle the current, so I went out and bought beefier diodes and bigger capacitors that would take the ripple out, and everything works just fine now. So that's the kind of stuff I do when I'm looking for ways to waste my time. You know, my retirement years. I haven't heard any questions, so assuming you got all the stuff pretty well figured out.
Before you erase it, is that the Wheatstone bridge-like diode arrangement? Is that the rectifier? Is that
is your bridge rectifier. And by the way, you mentioned you threw out a word there. So I might as well tell the rest of the audience what you just talked about. Wheatstone is a gentleman who came up with this concept. That you could hook up a network of impedances, and they don't have to be resistances. They could include capacitances, they could include inductances, and you could even do something else. You could put something here, although mostly what they put in the middle is a meter. And this is a device they use for measuring complex impedances, or even simple impedances. What they do is, you got an antenna, and it's a certain length. And you want to know how I can make this thing operate on a frequency other than the length for which it is cut. And you build something that's pretty much like a transformer. It changes the impedance that the antenna provides to match, the word match is key here, the impedance of the transmitting device. The generator and the load have to be matched in order to get the maximum power from the generator to the load. And to do that, a good way to start is measure the antenna and see what its impedance is. And this is the device that will do it. And you'll probably take one of these 4 corners and you will plug in your antenna there. And the simple rule is the means and the extremes will equal. This times this will equal this times this, and you'll know that they're in balance when the current flow through here is nothing. That's what that kind of bridge does. That's a Wheatstone bridge. The bridge we just did is called a diode bridge. And what we ended up doing is making sure I point all the diodes in the right direction. I'm going to tell you a cute little thing that I came up with where I used this in an unexpectedly different way than it was maybe often used for. You can buy some devices at Radio Shack and other places that are these four diodes hooked up just like this, and it will tell you that the AC goes in here, and the plus side will be here, and the minus side will be there. So you know exactly where to put your transformer's output, and you know where to pick up the plus and where to pick up the minus. And it's internally just like that. It's four diodes put together in that particular arrangement. Tell you what it's really nice for. I had to do a project for Zenith Electronics a long time ago where they said, what if people plug in, attach to the power source and they put it backwards? How do you prevent them from doing damage to the circuit? By reversing. I said, put a diode bridge in there. It doesn't matter if you plug into the AC part, it doesn't, because AC is constantly switching between plus and minus. It doesn't matter if my plus is here and my minus is here, or my minus is here and my plus is here. The bridge will make sure that this plus and this minus don't change. Interesting application for that. Bridges have all kinds of great uses. One for measurement, one for rectification. Glad you brought that one up. Any other questions? I want to hear more questions.
It'd be okay if the electricians wired the outlets all the same.
Well, wait a minute. Now's a good time to bring up that subject too. You got alternating current here. Does it really matter which wire goes to which of these two prongs? After all, it does go positive and negative. There's no positive and negative. It's constantly flipping back and forth. You might say, no, of course not. My answer is, no, it doesn't matter, other than a matter of safety. And since the subject comes up, I always talk about them when they do. The safety feature that makes for what we now call a polarized plug, if you ever look at the outlet in your house, if it's not more than 50 or 60 years old, you'll find that one prong is wider than the other one. So that when you take a two-pronged plug and stick it in the outlet, you can only put it in one orientation. And that's done to deliberately make sure that what is called the neutral side gets the narrow prong, gets the white prong, excuse me, and what is called the high side or the hot side gets the narrow prong. Why does that matter? Won't the device work anyway? Yes, it will work, but if you touch the wrong thing, you won't be working for long because it will set you up for electrocution. Let me demonstrate why that is. Your power company generates, actually they start out with a generator that produces about 15,000 volts. If you go to a power station, that's typically what a generator produces. With three separate windings, it's called three-phase power, where each third of an arc of the rotation of the rotor inside the generator has a separate set of windings for it, and it's done for a lot of good reasons. Maybe I should talk about that too. Suffice it to say, it comes out at about 15,000 volts. It goes through a transformer, gets boosted up to a high voltage. We know the story about that. Edison said, well, let's just use direct current, it's safer. And so what if you have to build a relay station, a repeater every couple of miles? I get to sell more dynamos that way. And a guy named George Westinghouse, listening to a very bright guy by the name of Nikola Tesla, and I remember in the first session the question came up, did Tesla really invent alternating current? And Greg Gleben said, I'm not sure, but I'll tell you the answer is yes, he did. He had a thought experiment while he was walking around New York Central Park, and he said, if I have an alternating current, I can produce an alternating magnetic flux. The magnetic flux, just like we did with the transformer, can change the voltage from a low one to a high one by the number of turns that are on the primary being the one that's the input, and the secondary, the output side of that transformer. And he sold this idea to Westinghouse, saying to Westinghouse, okay, here's what you're going to do. You'll come out of your generator producing the voltage it does, again, so it's around 15 typically, and you'll step it up. How much? Greg wasn't sure, I'll tell you the answer. The rule of thumb is about a kilovolt per mile. So if you're gonna go, and 750 miles is about as far as you can go without having serious copper losses. So if you're gonna go that distance, you're gonna step that voltage up to 750,000 volts. That's the transmission line voltage. When you get to a substation, you've seen those things. You got to drive down 41 in Northbrook, and it's off Skokie Road. Or if you're in Lake Forest, it's somewhere at the north end of Highland Park. Big field inside a fenced-in area full of transformers. And they take those ultra-high voltages, they step them down to what are called distribution voltages, the ones they send on the telephone poles, or if you live in a more, recently developed area through underground wiring. That could be anywhere, on overhead wires it's usually 12,600 volts. Underground wiring is typically 3,300 volts. And again, the same rule applies. Higher voltage means less current means less copper loss. Same power, because volts times amps is power. So put the voltage up, you can take the current down, transmit the same power more efficiently with less copper loss, because the copper loss follows that rule. That equation came from. Okay, you just substitute for I and you get I squared R, or you get B squared over R. Same idea. Current determines the power, and it's not linear because it's a square. It grows hyperbolically. All right, so what you do with the power company is you start out with the voltage they do. They transmit it at high voltage. They step it down to neighborhood distribution voltage, and right next to your house or somewhere on the block is another transformer that takes the distribution voltage and steps it down to 240 volts